started trying to talk about calculus on a Riemann surface. And so I want to kind of finish that since it'll be what we use in proving the uniformization theorem. And I think it's, if you haven't seen this stuff before, I'll go over it kind of pretty quickly, but it's really worthwhile to think about this. So it takes some getting used to more than any deep insight. Right, so remember, we were doing everything in sort of subsets of either R2 or the complex plane, and then the idea was if we check things were well behaved under, say, holomorphic transition functions, then they made sense. If they were well behaved under smooth diffeomorphisms, they were made sense on a surface, and if they were well behaved under holomorphic functions, then they made sense on a Riemann surface. Right, so again, we sort of said R2 is the same as C, where here we have x, y goes to z equal x plus I, y, and we're always going to just fix some phi that takes u to u prime. These are open subsets of R2 or C. Depending on how we want to think about them. Right, so we had these natural kind of vector fields, which were first-order differential operators, when we thought about things as a complex, the complex space. And I just wrote these as z, which was also ddz, and z bar, which was ddz bar. And the idea is this is 1/2. If you think of a function of a real variable, this is 1/2 when you take ddx. A function of a real variable, but taking, say, complex values, and this was the same thing. Okay, so these are sort of complex. These are kind of complex vector fields. So the idea is they act on complex valued functions of a complex variable and spit out another complex function. But you can also think of them as real valued functions of a complex valued functions of a real variable, and then these operators make sense. Okay, so then, of course, in a chart, we can check if something's holomorphic by applying the z bar operator and seeing if it's 0. Okay, that's just a reminder. And then similarly, we had these sort of dual objects, which were the complex valued forms. So these were dz, which was, of course, the same as dx plus I dy, and dz bar, which was dx minus I. And in general, for us, in general, a complex valued one form would just be some kind of some combination of these where we had complex valued functions in front. Okay, so the point that we made last time, which I just want to reiterate because this is the key to everything. So if you haven't seen this before, you should really dwell on this. Right? So if we wrote a complex one form as a dz plus b dz bar, right? So the a prime and the b prime were in this what might be called zero-valued complex forms of u prime, which is the same as just C-infinite functions of u prime that were valued in C. Right. So think of this as an open domain in the complex plane, but just to make sure just to think about it, you can go back and forth. It doesn't make any difference. The point is, in general, for a smooth map, if we just take the pullback of omega, one computes that this is the same as a prime composed with phi. We apply the vector field z to phi, and then multiply by dz, plus the vector field z bar applied to phi dz bar, plus right. So in general, even if we start with a form where this is only of, say, spanned by dz, where b prime is 0, if we just take a general function, we might start a general smooth function phi, we might get a term with z bar by this action right here. However, one can make sure that never happens by taking phi to be holomorphic, right? So if phi is holomorphic, right, this is essentially equivalent to saying that that the pullback of let me put it this way, of a prime dz is equal to some a dz, right, for a determined by the formula you see here, right? So you would get you get this term, and this term would be 0, and b prime is assumed to be 0, so you never see this term. But the point is, right, what you're supposed to understand from this is that we have this natural splitting, right? So we have this splitting of the one forms, the complex valued one forms of u prime into the 1, 0 and the 0, 1. And this splitting is preserved by only preserved by holomorphic maps. And so what this means is, of course, the only way to make sense of this splitting on a surface is if we have a Riemann surface. So the upshot is that on a Riemann surface, we can split the complex valued one forms of sigma, or let's call it x, into these 1, 0 part and the and of course, in a sense, I mean, one way of thinking about, at least for Riemann surfaces, one could wonder if one always had such a splitting, and that sort of was smooth in a certain sense, did that determine a Riemann surface structure? So it turns out for Riemann surfaces that's true, but it's a more subtle question more generally, where you might consider such splittings. That being said, I want to Hayo talked about this a while ago, but I mean, maybe to make it clearer in the simpler setting so people can try and see what this means in this context, right? I mean, the idea of being a holomorphic map is the same as being a complex linear map. So let me just make that kind of very clear in this setting and how it relates to this splitting, right? So again, on, say, open subsets of R2, or C, right, we have this natural linear map sort of linear J, which is defined so that J of ddx is equal to ddy, and J of ddy is equal to minus ddx, right? So it's it's a linear map. I mean, these are vector fields, so you should think of this as a linear map, which is varying based on the point, but it's the same at every point. So the observation is this is an endomorphism whose square is minus the identity, and I mean the thing you see is that one observation is just using, if you extend this to a complex, you complexify this, right? So J of C of Z, if you work everything out, is exactly I times Z. And J C of Z bar is exactly minus I Z bar, right? So in a sense, if you complexify J, then the Z and Z bar become the plus I eigenvalue and the minus I eigenvalue. So again, I mean, this is just we've already mentioned this, but it's good to see it. And similarly, if you take the dual, I mean, when you can act on vector fields. Once you can act on vector fields, you can dually act on forms, and you see that if you take the dual operator, then exactly the 1, 0 forms are sort of the I eigenspace, and the 0, 1 forms are the minus I eigenspace of the dual action. So you should check that, at least up to sign. I'm not good at signs. Okay, so then the point, though, is, right, what does it mean to say something's complex linear, then? It means exactly, you should work this out, but to say phi is complex linear, in other words, holomorphic, right, is to say that J composed with the differential of phi is equal to the differential of phi composed with J. Okay, you should work that out to check that, but it's true. So again, what this means is that on a holomorphic map, this J sort of, in a sense, there's a consistent notion of how to take this rotation. I mean, if you think about it, going back to, if you consider the Euclidean metric, this is like rotating by 90 degrees. So if you think about it, this map is sort of rotating by 90 degrees in the tangent space, and what one can take away from this is that this is, on a Riemann surface at least, this rotation by 90 degrees makes perfect sense. And so what one gets is, in general, on a Riemann surface, one has a map JP for each point P in X that takes the tangent space of P of sigma to the tangent space P of sigma, and JP squared is minus the identity. And if you take the dual map, which takes forms to forms of the cotangent space to the cotangent space, you can check that essentially, when you complexify it, the eigenspaces are exactly this splitting. And again, to connect this back to this thing we talked about earlier when we had this notion of a conformal structure, right? So that made sense. We had angles, right? We can measure angles, and so Riemann surface has a conformal structure, so you can measure angles, and it has an orientation, so we can say which way is clockwise and which way is counterclockwise. So what you should think of is, if you have that information, you can also get a J, right? Just you can kind of rotate everything by 90 degrees at each point, so clockwise, say, or counterclockwise, right? So the point is, you need the orientation to say what clockwise or counterclockwise is, and you need a notion of angle to say what 90 degrees is. So this is another way of seeing why that sort of, you would expect this Riemann surfaces to be kind of the same in 2 dimensions as sort of having a conformal structure with an orientation. Okay, so that's a different perspective. But I just want to make this kind of be pedantic about it, so you. Okay, so then, right, so now we have this notion of taking a derivative. I mean, so we know on a surface we have this exterior derivative which maps, say, smooth functions to smooth 1 forms, and then also smooth 1 forms to smooth 2 forms. So we might ask, what happens to the derivative now that we have this extra splitting? And of course, not surprisingly, it behaves well, right? So again, you can compute that that for a function f in, going back to just the open set in the plane with complex values, that if you look at df, then this is the same as z dot f dz plus z bar acting on f dz bar, right? So this is a a 1, 0 form, and this is a 0, 1 form. And so since we have the splitting, we can sort of break df into del f plus del bar f, where now we're supposed to think of del as taking these 0 forms of complex values on u prime to the 1, 0 forms, and del bar doing the same thing. Right. So again, we want to sort of see if this makes sense on a Riemann surface. And again, the main thing we need to do is check that under a holomorphic change of coordinates, this formula still makes sense. And so essentially, what you should check is that if phi is holomorphic, that say if you do the pullback of del f, that's the same as del of phi pullback of f, and similarly. Right, and essentially this just boils down to looking at this formula here and working everything out. So I leave it to you. But that means that on a Riemann surface, right, we get this this picture where we have sort of here's the 0 complex valued 0 forms on X. Then we have, again, you've seen this already, but repetition is good, right? So this is the del, and this is the del bar. And taken together, these things give us d, and we can compute d by just taking del of the guy and adding del bar of it. So we have d. There's a sort of d map here, which is equal to del plus del bar. And similarly, we can try and take the look at the same situation where now we want to see what happens when we take d of a form here, right? But the point is, you should check is that the right. Again, going back just to the surface, so in coordinates, you can check that if you look at omega 2c of u prime, right? Right. So this is supposed to be the span of a complex valued function times dx dy. You can see that this is really one complex dimensional. Well, at each point is and the idea is that a general term in here is going to look like dz wedge dz bar, where this is the same as if one works out just from this formula and the sort of anti-symmetric properties of the wedge product, this would be minus 2i dx wedge dy. Sorry. Yeah, minus 2i. Dy. Right, so, and then again, what one works out is if we can take d of this again, but of course, one has to sort of check this, but it should be kind of clear from the algebras that if you take del squared, that's the same as del bar squared is equal to 0. And so when you compute d, you can really think of you're computing just del bar, and here you're computing del, and you get to omega 2c of x, which sometimes you also would, if you wanted to emphasize that you're working in this Riemann surface, you would write it 1, 1, but that's not really telling you anything. And the observation, of course, is that in coordinates, for example, del bar of f of z dz is equal to, say, minus del bar z f, so to say z bar acting on f, dz wedge dz bar. And similarly, del of, say, g of z dz bar is equal to del z acting on z dz, wedge dz bar. Okay? Okay, so then the final thing that this allows us to do is to see that suppose we start here with a 1,0 form, right? So if we have a 1,0 form and we take del bar of it, that's the same as essentially taking, in coordinates, taking the del bar of f. So this is going to vanish precisely when f is holomorphic. And what one can check is that this is well defined independent of holomorphic change of coordinates. So we can make a definition now of a holomorphic one form. So we say a one form, a 1,0 form. So in other words, an element of this guy is holomorphic if and only if this del bar, let's call it omega, if and only if del bar of omega is equal to 0. Okay, so right, and again, by what I just said, it's easy to check that a 1,0 form is holomorphic if and only if in local coordinates it's a holomorphic function times dz. Okay. Okay, so now the next thing I want to say is, so as maybe I should mention, we'll come back to this. So you might wonder, we have a notion of holomorphic function, and then we have a notion of meromorphic function, which is you should expect that there's a notion of meromorphic one form. Of course, to make that completely nice, you want to introduce some more fancy stuff like line bundles and so on. But since we're in a pretty simple situation, just as we could think of meromorphic functions as maps into the Riemann sphere, it's not too hard to define a meromorphic one form or 1,0 form to be a 1,0 form which in local coordinate has a discrete, it's a holomorphic away from a discrete set of points, and in local coordinates in a neighborhood of any of those discrete points, it's of this form where f is meromorphic. And then one has to, of course, check that's well defined, but that's a simple exercise. So as we'll see, I'm trying to understand the behavior of, say, meromorphic or holomorphic. The counting the number of these guys, in some sense, is important in understanding the topology. Well, it's closely linked to the topology of X. In some sense. So we'll come back to these next week. But moving on, the final thing that's going to be useful to have right, is the right. So as I said, on a surface we get these natural operators, which are the D operators, which go from 0 forms to 1 forms and from 1 forms to 2 forms. On a Riemann surface, we can refine these, and these are all kind of first-order operators in the sense that they involve one derivative. So on a Riemann surface, of course, we can split these operators. So we get these two related operators, del and del bar, which are again first-order operators. But the interesting thing is here, in a smooth surface, if you take D and then you apply D again, you get 0. That's easy to check. But you should observe that if you apply del and then you apply del bar, you can't be sure you get 0. I mean, if you apply del and you go to del again, you do get 0. Or if you went to del bar again, you do get 0. But you don't get 0 if you go this way. So what that means is on a Riemann surface, you have a very natural second-order differential operator. So on a Riemann surface of a natural second order operator. Right, so that's, we're going to call this the Laplacian, and we'll see why in a second, and this will be by definition basically what I said, going del bar, but with just a slight normalization. So it's, and so this takes, complex valued functions of x to two forms. Right, and the reason we call this the Laplacian is you should check the in a local coordinate chart, so or on U, well, in local coordinates, right? We can compute del of f is equal to one should check this, but it's true. It's 2I times z bar of f dz wedge dz bar. What is that? Sorry, I think this might be. I think this has a sign mistake. So one should check that this sort of doesn't depend on the order you make it, but let's do it this way. So this is correct now. And so then if we expand out z as a half, x plus iy times a half x minus iy, and you do everything out, right? So 2I times dz wedge dz bar. Did I erase that? Sorry. Yeah, wait. I'm being completely blind. The 2I times, so 2I times dz wedge dz bar should be 4 times dx dy, and then this is, you should work out as 1/4. So this is supposed to be equal to 1/4 d dx squared plus d squared dy squared dx wedge dy, unless I made a mistake, which is highly probable. Yeah, so then the 2I times the minus 2I is supposed to be 4. So we're supposed to get the Laplacian. Okay. Sorry? F, yeah, of course. Okay. Right, so this is our usual Laplacian. Of course, Laplacian always has this, I'm a little, one should be really careful about the sign. I mean, in the end, it doesn't matter too much, but if you're not careful about it. So this is the sign convention I prefer, right? So sometimes people put a minus here, so the integration by parts is nicer, but I prefer it with the plus, because that's what I'm used to. Okay, so this is the, in local coordinates, what you get. And right, so this is the justifying the Laplacian, because we're just taking the normal Laplacian. But the point, going back to this connection with sort of conformal structures, right? You should observe that if you have a metric, if you have a metric G that's sort of compatible with the Riemann surface structure, right? So in the sense that we discussed at the beginning of the class, or more, right now it's very easy. You should convince yourself it's true, but it's not hard to see. I mean, the metric gives you a natural J, and the Riemann surface structure gives you a natural J. So those two are the same. One should check that this Laplacian of f, in our sense, is the same as taking the Laplace-Beltrami operator of G of f and then multiplying it by the volume form of G. Right. Right, so notice this is an operator of functions to functions, whereas this is an operator from functions to two forms. So the point about all of this, as we'll see shortly, is that right, in dimension 2, the Laplacian is sort of conformally covariant in the sense that conformal changes of the metric only change the value of the operator by scaling, and you can precisely capture that scaling by putting in a different line bundle, right? So, right, you can think of this as mapping the sort of bundle of smooth functions to the bundle of smooth functions, whereas this is mapping the bundle of smooth functions to the bundle of two forms. So we'll see that this is reflected in a kind of nice computational property of the Laplacian in a second. Right, and of course, to make sense of the volume form, we're using that it's oriented. So always remember that. Okay, and just a final kind of definition, right? Right, we say a function u on x is harmonic. So it could be real valued or even complex valued, it doesn't matter, if and only if the Laplacian of u is equal to 0. Okay, so we don't have any, I mean, we have a special section of the space of two forms, which is the 0 section. And then the observation is that, of course, if f is holomorphic, and then the real and the real part of f and imaginary part of f. This is a classic fact in complex analysis, but is also true in Riemann surfaces are harmonic. And what you do is you just, the real part of f is just f plus or minus, this is just f plus or minus f bar, this is up to a constant, so a half or 1 over 2i. Well, let's so maybe rather just say this guy is obviously, if you apply del bar to it, since f is holomorphic, the del bar gives you 0. And since this f is holomorphic, then del of f bar is also 0. So then you see that this guy is harmonic. And these two are just these up to multiplication by constants. Okay, so right. So one silly observation, though, of course, there's much more revealing ways to prove this, is that since they hold much more generally, is that if you have a harmonic function on a closed Riemann surface, then it has to be constant. Sorry, that's not. That's true, but to see that we need the other, we can't actually see that from this. So to see this, what we need is actually the other direction, which I'll get to, maybe give you as an exercise. So we want to say that if we're given a harmonic function, whether it's the real part of a holomorphic function, so that's a kind of question you could ask, is a real valued harmonic function, is a harmonic function the real part of a holomorphic function? So you probably remember from complex analysis that in a domain in the plane that's simply connected, so a disk, this is true, there's always a so-called harmonic conjugate. So one is not surprised that that's also true locally on a Riemann surface. But what we'll see in a second is that there's actually globally obstruction. So you can't always get a harmonic function globally as the real part of a holomorphic function. Of course, as I just said, on a closed Riemann surface, there aren't any harmonic functions, but there's also no holomorphic functions that are not trivial. So it's a bit of a vacuous problem there. Okay, so let me just try and slightly motivate where this Laplacian is coming from. In a way that will allow us to prove some properties of it. Ultimately, we're going to approach the uniformization theorem by proving, understanding under what conditions we can invert the Laplacian, because that'll allow us to find lots of interesting, say, meromorphic functions, which will be important in our proof. So to do that, we need the following notion of the Dirichlet norm, which, of course, you probably have seen in the context of just in Rn, say, but we'll be able to see that there's a nice way to do it on a Riemann surface sort of invariantly. So what's the idea here? Right, so we note first that there's a well-defined, we have a map from the 1,0 forms of x on a Riemann surface to the 0,1 forms of x, given by omega gets sent to bar omega. Okay, so that's easy. Just check it in local coordinates, but it's clear. And so what that allows us to do is we can then define then given from this, so observe that for an omega, a 1,0 form of x, these are complex valued, we can look at the following object, which is the wedge product of wedge omega bar, times, say, let's just put 2i for the moment. Right, so if we work this out, right, if we write omega locally as p of z, d of z, it's not hard to see that this is actually equal to 2i times p squared, the norm of p, dz wedge dz bar, which is equal to 4 times p squared dx wedge dy. Right? So the point is, this is, at least in the local coordinates, this is sort of positive in the sense that if it's the volume form times a positive number, or a non-negative number. Right. I mean, one thing to take away from this is if we have an oriented surface, right, there's a notion of positive 2 form, and this would be a positive 2 form. And since this is going to be preserved under, or non-negative 2 form at least, and since this is preserved under orientation preserving change of coordinates, we actually see that this is sort of a positive object on a Riemann surface. So the idea is if we form the following norm on the space of 1,0 forms, right, we can compute this to be the integral of x of 2i alpha wedge alpha bar. And the point is this is greater than or equal to 0 everywhere. Of course, this could be infinity if x is non-compact. Okay, so we allow infinity, but then we could say like the space of, say, L2 0,1 forms would be the set where this is finite. And of course, with L2, with the completion of the set where this is finite under L2 convergence. Of course, one thing to observe is if you're compact, then this is always going to be finite when you're smooth. Okay, so that's the Right. The point about this is that we haven't normally when you want to define a norm on a norm on a vector space, right? You need to choose some. A norm on a, say, a manifold. You need to choose something like a metric or something, or at least a measure. But here we get it for free just by having the Riemann surface structure. So that's sort of the point, and it's going to, as we'll see shortly, it'll be connected to this existence of delta. Okay, so now, right, one should you should convince yourself there's also this Hermitian inner product, which is just going to be equal to 2I. But now we have at least where, like, say, let's say alpha has compact support. Right, so, this doesn't have a sign necessarily anymore, so we need at least one of them to be compact so we can form the integral. So this is the Hermitian inner product. Okay, so then the observation is, right, we can now form an inner product on the space of real one forms by doing the following, right? So given a real one form omega, we denote by omega 1, 0 its projection into omega 1, 0. Right, so if we have a real one form, right, it's just as it's a one form. We have a natural way of talking about real valued one forms by just taking normal one forms and then, tensoring them with one, thinking of them as complex valued. But we want to sort of project it into this 1, 0 space, so we can apply all of this. And just as a care, right, if we take in local coordinates that omega is equal to dx, then this omega 1, 0 is equal to a half dz, right? Because this is because dx is equal to dz plus dz bar divided by 2, right? Okay, so then we can again define the analogous thing. So and the point, though, is that this gives us a useful semi-norm on, say, smooth real-valued functions. So let's suppose f and g are C-infinite functions of x with values in the real numbers, right? So we define what's called the Dirichlet inner product, right? So this is just by definition going to be, well, let's say they have compact support. So this will just be the this Hermitian inner product of df 1, 0 dg 1, 0, okay? And one can see that similarly, we have an associated norm going back and forth, the Dirichlet norm, or semi-norm, which is just going to be, say, the integral over x of 2I of df 1, 0 wedge dg 0, 1. Okay? And the point is, if we've done everything correctly, which I'm not entirely if we've done everything correctly, this should essentially agree with our normal Dirichlet energy for a function, right? Where the metric we use to define the Dirichlet energy is precisely the the metric G that's compatible with the Riemann surface structure. And the whole point here of why we're able to do this solve so invariantly is that in 2 dimensions, the Dirichlet energy is conformally invariant, which is very important in its analysis. Okay, so so I'm a little afraid of sign issues. So you should maybe, as an exercise, check that is equal to the integral of x of what you would normally expect, which is the gradient of f with respect to a metric G compatible with the Riemann surface structure squared, d vol G. Okay? So, but I'm a little afraid about this. This should be true. This should be true. Everything should be positive, unless I've messed up. Okay, so check that, and maybe there's some constant here, but that's just a normalizing factor. So again, if you recall, I mean, the point is if you conformally change the metric here, this scales like the conformal factor, and this squared, and this scales like the conformal factor to the -2, so the 2 conformal factors cancel out. Anyway, going back to this inner product, right? I mean, here you normally can use this Dirichlet energy to see how to get the Laplacian, because of course, the critical points of this energy are exactly going to be weakly harmonic functions, and so we can see again that this Laplacian here is going to arise from this guy by variation. So this is maybe an exercise as well, is to check that if we take F and G, D, where these guys again have compact support, that this is equal to, with a minus now, assuming I got all the signs right, the integral over x of F Laplacian G, which is the same as the integral over x of minus G Laplacian F, right? And the idea is this makes sense because this is a 2 form. So we can multiply 2 form by a function and integrate it. Okay, so, and again, one can check that if you take kind of critical points of this, by this formula, a critical point of this function with respect to compactly supported variations is exactly a function which is essentially harmonic. So, but the point is this makes sense, as we'll see eventually, this makes sense fairly low regularity, and so that gives us a notion of a weak solution or a distributional solution. Okay, so now in the last 10 minutes, I just want to briefly discuss de Rham theory, which is getting back to sort of this question about when is a harmonic function the real part of a holomorphic function. Okay, so for this discussion, we'll work back in just the real setting, and then when we need it, we'll talk about the complex setting, which for surfaces there's very little that's different, so I don't want to dwell on it. Right, so again, remember now we just have sigma a surface, so not necessarily a Riemann surface, but certainly any Riemann surface is a surface, and we have the functions. This is the C infinite functions. Then we have this differential to the 1 forms, and then we have the next derivative to the 2 forms. And the point is, if we take the composition, this is 0, which again we checked. So the kernel of the kernel of this map are called the closed forms, and the image are called the exact forms. And the question one always is sort of interested in this case is, to what extent how much bigger are the closed forms than the exact forms? Because you can check whether something's closed fairly easily, but it's a little bit tricky to check something's exact. Okay, so right. So the point is, and everything here is nice and linear. So we have these following important linear spaces, which are the first de Rham cohomology, H0 sigma. This is equal to the kernel of the map. Let's just for the time being call this D1 or D0, and let's call this D1. This is the kernel of the map D0. So these are the functions whose exterior derivative is 0. And the point is, you should convince yourself that these are functions which are locally constant, right? So this is it's pretty clear this is isomorphic to R when essentially if and only if sigma is connected. Okay, so there's nothing really interesting happening here from some point of view. So the second group, this is the first group. The second group, or maybe this is the 0th group, and this is the first group, is the first de Rham cohomology group. So this is, of course, the kernel of D0, right? Which the kernel of this, D1, the kernel of this contains the image, so we quotient out the image, and this exactly measures the how many in some sense how many closed forms there are that aren't exact. And as we'll see, this is actually where all the action is for surfaces that are oriented, at least. The final, and that's not surprising. There's not that many different surfaces, and we expect this. One can check this is all a diffeomorphism invariant. And so the final group is the H2 of sigma, which is equal to the space of two forms of sigma mod the image of D1. Okay? So this is sort of interesting in the following case. So one thing you should convince yourself of is that it's, well, let me not get too far into it. All right, so one thing you should convince yourself of is, let's suppose sigma is oriented, right? So if sigma is oriented, you can integrate every two form over the surface. And so it's oriented and closed, so you can integrate every two form over the surface, and that gives you some number. And because it's oriented, you know there are so-called positive two forms whose nowhere negative and everywhere positive in the sense that you check it in local charts, and so that you can get guys whose integral is positive. On the other hand, by Stokes' theorem, these are all the images of one forms, and if you integrate the image of a one form over a surface, you get 0. So that means that on a closed oriented surface, this map always, this group always surjects onto, or vector space always surjects onto the real line. And again, one can check, it's a little bit more involved, so I don't want to get into it, and it won't be so relevant, but one can check that actually on a connected compact oriented surface that this guy is R. On the other hand, on a non-oriented closed surface, this guy is 0. And then on a non-compact surface, one sort of expects that it's a little bit, maybe just to convince yourself it can be 0, just consider H2 of the plane R2. So maybe just an exercise, prove that this is equal to 0. The idea is, given a two form, you can use a kind of integration to find the one form whose d of it is sigma. But sometimes one doesn't like one. This is somewhat annoying. So sometimes one restricts to compactly supported forms where everything continues to make sense, and one gets the compactly supported de Rham groups. And then this argument I gave for the closed case also works in the non-compact case as long as you're oriented. So you can actually get a similar result there. But that's maybe getting too far afield. But the point, though, I wanted to make is that this is where the interesting stuff is happening. Okay, so the first computation, which maybe again, I'm sure most of you know this, so the people who don't know this, maybe just ask someone who does and work it out. It's good sort of some good exercises, right? Right. So one computes. Right. So first of all, the h1 of R2 is equal to 0. That's pretty clear. On the other hand, the same thing is true as h1 of S2 is equal to 0. So one way to see this is to think of S2 is equal to S2 minus the origin union S2 minus infinity. So these are both copies of R2, and then use the definition of what this means and the fact that the overlap to sort of prove that on the overlap here for any closed one form you can find a primitive, and here you can find a primitive that is a function whose d is that one form, a function whose d is that one form, and then on the overlap you can prove that they have to essentially the difference has to be a constant, and so since you can adjust any function by adding or subtracting a constant, you can actually extend the primitive here to infinity, and so see this. But that's a good exercise to go through this. So of course, on the other hand, one can compute that say the annulus, so the punctured complex plane is equal to R. And the way to see this is you have let's just take the punctured disk, which is topologically the same. Pick this curve gamma, right? And so then you look at the integral around gamma takes omega 1 to the real numbers, right? These are real one forms. And you can check, again, just by, this is almost by definition, but you should, the integral of a closed one, of an exact one form over a closed surface is always 0. So then this is clearly a surjective map because we can just construct an example, and then you should convince yourself it's an injective map. Then in general, once you know this fact for the annuli, it's not too hard to convince yourself that the h1 of sigma g is equal to r to the 2g. So I'm out of time, but let me just draw the picture that should try and convince you of that. And maybe an exercise is to work out the details. Right. So remember we have sigma g is you take this torus and you just connect summit with several copies of the torus. So we have these distinguished curves, which is like gamma 1 and then say eta 1, and we can repeat that here. So right, and so then you can sort of get a map. So you get a map from right. So my point is this descends to a map from h1 of R. Right. So then from doing the same argument, you get a map from a sort of integral map over, gamma 1 up to gamma g, eta 1 up to eta g, from that takes the h1 of sigma into r to the 2g. And so by using the ideas here, you can kind of construct one forms that have to prove this map is surjective, and then you have to do a little bit of convincing yourself, but to show that it's actually injective. But I'm out of time, so I'll stop here. But again, the point is that somehow the genus is now showing up in calculus, which is the upshot of all of this.